So moving on again, let's just recap what rasters are. You should have already encountered all of this, but let's just go over it one more time to make sure. Let's get it back into our heads so that we're aware of what rasters are and how they work. So we have a raster. As we saw in previous slides, our raster consists of cells stored as a number of rows and columns in making a grid. The cells are generally speaking square, not always. Sometimes we have oblong, rectangular, however you want to describe it, cells, particularly when we're looking at, say, data stored in longitude and latitude. But they also have other shapes entirely as well. We're not strictly speaking bound to a rectangular form, square form, but generally speaking they are. In most cases they are. And each cell can store one value, and only one value. If we want more information at a particular cell, then we have to create an entirely new layer, an entirely new raster. It might be stored within one file, in, say, the case of an aerial photograph or a satellite image where we have different color information, the blue, green, red, infrared, of different wavelengths. But each image is a grayscale image stored as a layer within that raster. And for continuous data, that's generally speaking fine. When we have, when this is continuous data, color, elevation, that sort of thing is continuous data. If we have discrete data, classes of data, information like this, roads, railways, or soils, or crops, that sort of thing, land cover data, that's all classed data. It's discrete classes. There's nothing in between. What's halfway between a road and a railway? Okay, there's a crossing, of course. We could, but there's degrees of being a road or a railway. It's either a road or a railway. It's very difficult to see both at the same time. Even if somebody, I'm sure, could try and find an exception. But let's just say it's classed data. I believe there's a bridge in Norway that's both a road and railway bridge. Norwegians. But so we have our class data, and this means that there's nothing in between. It's discrete information, and therefore, if something doesn't belong to any class, there's just nothing there. Well, what are we going to do? Because of the way raster data is stored, we actually have to store the information. There's nothing here. There's nothing here. There's nothing here. There's nothing. So kind of inefficient in that sense with this classed data. So because we build up our raster image by taking a cell and then implicitly locating the next cell next to it. So we're getting the information stored on the computer saying, next piece of information, slide that along, put it next to that cell. Next piece of information, slide it along to that cell. And we count up how many times we've done that. And when we've got the number of columns right, okay, stop, next row, slide the next one in, and then slide the next one in. There's not explicit information about that location. It's all implicit, which means that we actually need to have the cell in there, even if it's got nothing in it. We need to say, oh, here's an empty cell, slide that one in. Here's an empty cell, slide that one in. Otherwise, we won't know where we are, or the computer won't know where it is. So discrete data looks like this, sort of. Here we have a couple of points and a polygon and a line here. So maybe these are houses and this is a lake and this is a road. And we can see that here we have our cells. We have a 0 there. Nothing here. There's nothing here. There's nothing here. There's nothing here. There's nothing here. Something happens and it's a 2. And because it's discrete data in a raster, these cells are essentially ignorant of each other. These don't know that they belong together. We can look at this and say, well, that's a line, obviously, according to us, with our big brains. But otherwise, this is not really known as being an object, a thing. It just happens that these cells belong to the same class, whatever that class is. Class 2 in this case is a road, presume a green road. And then class 3 here, all of these belong to the same class. Now, there are ways of finding out that these all belong together. We can do some basic analysis to clump these together and say, oh, they all belong together. But essentially, they're ignorant of each other. These cells exist on their own and don't care about their neighbours. Continuing with discrete data, other qualities that they have when it comes to resolution, spatial resolution, we can lose things because of this discrete quality, and something is or isn't. And whether it belongs to one class or another class or a third or fourth class, or whether we just have the binary condition yes or no, it doesn't matter. In this case, when we look at this, what we have is an object. And in each cell, we have to make a decision. Is this a white or a red cell? Well, we can set a rule saying that if there's the tiniest bit of red, then it's red, but then why wouldn't it be white? We don't know what the white class is. So depending on how we set up our rules, basically what can happen is, well, the most dominant class here, clearly the most dominant class is white, so this is a white cell. This is obviously clearly dominated by the white, so this is a white cell. This is clearly dominated, you get the idea. And what happens is, because of our spatial resolution or the cell size, that object just falls out, just goes away. It's not there anymore. It doesn't exist. We have not the resolution. We cannot resolve that object. It's not there. If we increase the spatial resolution, or the ground sampling distance sort of thing, spatial resolution is a very difficult concept. We then start to see the object. It starts to exist, because it starts to dominate. Because the cells become that much smaller, there's a greater chance of our object dominating within a particular cell. And then the object becomes more and more clear and distinct. Its form begins to be more recognizable without increasing resolution, which takes more space on the computer, but there's our object. Going from the discrete case to the continuous case. So in the discrete case, we had something was or wasn't belonging to a particular class, or was true or false, on or off, depending. And so we have this Boolean state. But with continuous data, things can exist by degrees. Something could be true, or it could be false, or it could be somewhere in between in a bit of a grey area. Or we could have continuous data such as elevation data. So we start off at 0 and then we gradually work our way up, getting bigger and bigger. Or we have color, the strength of light, the color data, like the spectral image, whereby the strength of the signal is encoded as a continuous surface. So it's continually varying from weak to strong signal strength. And this may be represented as floating point numbers or as whole numbers, just very large whole numbers as well. This is quite usually the case, actually, that for remote sensing data, we don't store the strength of the signal as being a fraction of 1, but rather as just being some whole number, integer number, ranging from 0 to maybe 255, or much larger numbers depending on the source of the data. So we have this continuous data, and here we are looking at elevation data. This isn't actually a height above sea level, this is actually a hillshade, because if you look at elevation data, just a DEM straight off, kind of boring and difficult to see anything in, kind of fuzzy, just not very interesting looking. Whereas when we use a hillshade, start throwing shadows across, we can see details and they become more interesting. There are objects in this that we can see things. I know about this, where this is, and I know what we can see here. But this is actually a glacier here, and here we have bedrock, and here we have just these linear features of where the glacier is pushed across the till at the front here, and here we have a pushed moraine at the front here, and we have a lake of water. Of course, I can see these things because I was there and made some measurements, but I think it would be quite difficult to make that interpretation if you weren't aware of this, because that information isn't in the raster. It's just grey stuff. It's a continuous field, it's continuous data. You have this raster image with various levels of grey, and that's it. That's what a raster is. Further interpretation of that we have to do using our brains in many cases. The thing with a very important quality with continuous data, though, is that we tend not to lose objects as easily. It can still happen, but if you remember in the previous case, we had the situation of two classes, something existed or it didn't exist. Here we can have degrees of existence. So we have this grey background and the red object here, and it kind of influences what's going on in this cell here. We can see that it's mostly grey, but there's a tinge of red coming from that. In terms of remote sensing, there are other things that might cause that, but let's just not think about those for now. That's just the proportion of that that's in that cell. And likewise here and here and there. So the object doesn't disappear as such. We can see that something's happening there, but we couldn't possibly make out the shape from that, or we could maybe make a very, very approximate guess. And then as we increase the resolution, the same thing happens. And we can see that here, this cell, obviously there's no influence from the red there. And increasing cell size, so on and so forth. So this is because we have continuous data, so there are degrees of it being in a particular state, or degrees of existing, rather than our discrete case, which was absolute. Yes or no, either is or isn't. We've been touching on the idea of resolution and accuracy, whether things are there or not. We need to be very careful now. We're going to look at concepts of precision and accuracy, and we're going to take them up specifically in the context of rasters, because there's something quite important with rasters where we have this idea of continuous data, which feels like it's very exact, and we're getting a much better representation of the truth. But when it comes to rasters, we have a problem. So here we have a raster, and I've just chosen a cell size, 1 meter by 1 meter, square cells, and that's a raster pixel. It could be smaller or larger. What is precision and what is accuracy? Here we have the position of this corner stored with very high precision. We have lots of decimal points here. We're saying that that corner there is at this position exactly, with that precision. And that could be accurate. That could actually be true, that that corner really is there as well, which is one of these difficult concepts. What is the difference between precision and accuracy? Accuracy is how close to the truth, we can say. The definition exactly of what accuracy is varies depending on whether we're having trueness as well baked into our concept. Precision is always this thing, how many zeros or decimal places are there. Accuracy tends to vary, but accuracy is how true is this, we can say. Let's just call it that for now. And so we defined our position there. That corner, that is very much definitely there. And even the center of this cell or this pixel, well, we can define that with great precision, same precision as before, and that could be very accurate as well. The center of that cell is definitely there. Okay, and we can see that center is halfway up because we have 1 meter size pixels, and obviously we just add half a meter in each direction. That gets us to the center of the cell. A very easy calculation to make. So our precision, we're down to this level where we got this last decimal place there. Very high precision, great. But where's our information? We don't know where the information actually comes from. If we think back to the previous slides, we had a little bit of red down in the one corner here, and that was creating the color. That was what was making this whole cell slightly red. The information wasn't in the middle. It wasn't in that corner. It was over here-ish. And in other cells, it was sort of mixed in all over the place. But once we get to the raster cell, like this, we don't know where the information came from. It exists in the entire cell. Just over that entire cell, that's where it is. No matter how precise our position for the cell is, and how true that position is, the information stored in that cell, well, where is that? Our accuracy then becomes much lower. So this information could if it was actually down here in that corner, somewhere in that corner, well, we're saying it exists there, depending on how our data is stored, or is stored there. We've got an accuracy of perhaps, well, half of the diagonal across there. I mean, which in this case is 1.414 divided by 2 is approximately 0.7 meters. If the information is there, potentially it could be there. I mean, it could be in the middle. It could be over the entire cell. We don't know. That is unavailable information. It's not stored for each cell. If it were, then we'd be increasing the resolution. We would still end up with that problem again, just at a smaller scale. So this is the difference between precision and accuracy, and how we can think of the different parts of the accuracy within a raster data set. Even if our positioning of the raster itself and its structure, this grid, as it were, is very precise and indeed very accurate, the information within each cell need not be as accurate. And then, just to summarize the actual structure of the rasters, we have to have data in every single cell because of the way we're building up our raster. It's implicit, not explicit, so we're sliding along each new value and we have to build up. We don't have coordinates for each cell. We have coordinates in one corner and then some instructions as to how to continue the instruction. We have this idea then of needing no data, or null or nan, not a number, so that we can fill in these empty cells. So that there's something there, there's some kind of content that gets put into our construction so we can build up cell by cell by cell. And it has to mean no data. We cannot confuse it with 0. So this is particularly important when we're working with continuous data, because 0, as you can imagine, could be a value, could be something that means 0. Oh, our signal strength was 0 here. Whereas no data means we didn't even measure, or maybe we measured but we're not telling you, or this is irrelevant, it's just out of the system, it's just not 0, it's no data, it's not there at all. There's no measurement for you to read here. No data, rather than 0, meaning we actually registered 0 here. So this is relevant, this connects in when we start looking at calculations and manipulating data. We need to think about what we have in the cells, which we'll be getting onto in the next section. These calculations can be simple mathematical calculations based on each cell. So a cell by cell, we take the first cell, multiply it or divide it or add to it some value. That value, what is that? If we look at this last row here where we multiply, we take 2 layers and use the information from 2 layers together. So for Ndvi, Normalized Difference Vegetation Index, we look at the value in the red layer and the value in the infrared layer for a particular cell or pixel. In this case, if it's Ndvi data, we look at the values in one pixel and the values in the same pixel in a different layer, and then a combination of those two in some particular way, band ratio, that will give us a new value in our Ndvi raster. So that, in a sense, is kind of similar to the cell-by-cell value, whereby we're working on it from the data from one particular pixel or cell, but we actually happen to be getting another piece of our mathematical equation from a different layer. And then this one in the middle here, several neighboring cells, or a kernel, a moving window, a neighborhood. And we can use the information, rather than from different layers, from the cells or pixels around one particular pixel. So we do a neighborhood analysis. We look at the collection all in one area and do some maths on that and come up with a new value for the pixel at the center of that cell, or the center of that window or kernel.